just continue? Yeah. Thank you for the kind introduction. So today's talk, I think, kind of fits into the sort of topic, or not topic, but the aim of the workshop that you mentioned, Bethan. That, you know, when I was asked to contribute, the first thing that came to my mind was future. And this is not something I know much about because I'm not a computer scientist. And what I'm going to talk about today is going to be like from a user perspective, and I'm probably going to say things wrong, you know, in the eyes of a computer scientist who actually knows what's going on. But I'm pretty excited about future because it makes me more efficient in my daily work, and I hope to show some examples on how it can make everyone else more efficient in their daily work. So I'll go ahead. One moment. There we go. So parallel computing is something I guess many of us have heard of. And most of us, even at our laptops, have a decent number of cores. Like if I do parallel detect cores on my MacBook, it returns 12. And many of us also have access to, for example, high performance computing environments, and also cloud computing services like Amazon Web Services, Azure, Google Cloud, and so on. And sorry, just no problem. So it's also important to understand how we can make use of this, which is probably a good idea in many cases. And the type of parallelism that I'm going to talk about, or there are two types of parallel computing. You have hard problems and you have easy problems. And the hard problems typically involve like doing numerics in parallel. Like if I fit the GLM in R, like this line of code, it runs sequentially. And figuring out how to solve this, or how to fit this model in parallel, is a hard problem. It involves math. It involves understanding the underlying numerics. And that's the kind of domain that, for example, Apache Spark and Revolution Analytics and so on are really good at. And it's really hard. But then you have the easy problems. And that's like when you instead just want to fit the same model many times with different data. So for example, here I do the empty cars dataset, which is one of the built-in R datasets. And I split it by gears. So how many gears do the cars have? And then for each of those splits of the dataset, I fit the same model. So in this case, I do a apply, but I just call this same model many times. And that's the kind of problem that's easy to parallelize because you use the same code, do the same things many times. And in principle, it can be just spread out, and you can use multiple cores rather than running it once at a time. And today's focus is on easy problems. And these are often also called embarrassingly parallel problems. But they're still not always trivial to like understand how to implement it in practice. So, and parallel computing with future. So future is a package that was developed by Henrik Bengtsson. He is a member of the R core team, no, at least a member of the R Foundation, very senior R developer, and also an associate professor at the University of California in San Francisco. And this future package is becoming very popular. For example, he had a paper now in the R journal, recently accepted, where he cites that as of July 2020, the future package has 129 direct reverse package dependencies on CRAN bioconductor, which means that there are 129 at least packages that depend on future. And this number has probably grown since July 2020. And for those of you who have done parallel computing in R previously, for example, with Snow and with the parallel package, you might wonder why you would like to use future. And some of the advantages of future compared to those other packages is that they allow the same code to run on exactly the same, to return exactly the same results, no matter which platform you run it on. It works on Windows, it works on Mac, it works on Unix, it works in the cloud, it works on a computing cluster, and it returns the same results and has the same code. And also, it doesn't cause your R session to crash all the time, which was a problem with many of these other more older parallel computing packages in R. And actually, like recently on April 1st, the Futureverse was launched, and that was a website which describes this whole future framework. And you're not likely to actually use this future package directly, but rather one of the wrappers that they built that uses a more high-level approach to parallel programming. And then you don't need to care about all the nitty-gritty. But the website there is futureverse.org. And I'll introduce many of the components in this Futureverse today as we're talking about how to solve data science problems. So,
can I ask a question actually from myself about, because I've only used the parallel package, but in a very limited way. So if I run that on a different machine, you're saying it would give different results in the sense that the time would be different, or in the sense that it might crash, or which way does it give different results?
For example, it could, for example, be that the random number generator on Windows works differently than on Mac. Or it could be that it was not, for example, it may not be possible to run it sequentially if you use the parallel package. Like you need to actually make a cluster, whereas Future by default always runs in parallel. But I think I'm not honestly not entirely sure about all of this, but I think it has to do with random numbers. That you have to make sure, like, random number generation in parallel is not that easy.
Okay.
So I think that's part of the problem. And also that it also works on lots of different platforms. So maybe I'm exaggerating a bit here, but maybe most of it is that it actually works on lots of different platforms without changing the code.
And someone said in the chat, I mean, you can pass seed into these packages, obviously, but sometimes you do actually want the randomness there, I suppose.
Exactly, but if you pass the seed, then still, you know, if the parallel programming package that you use starts up, like, say, 100 new R sessions, then they may not remember the seed. They may not know the seed. So it may still not give exactly the same results as if it was run sequentially at a single core. And you cannot set the same seed on each worker, because then you will get exactly the same random number. If you know what I mean. So parallel computing with random numbers is pretty hard.
Yeah, I misunderstood. So Igor said, with Future, you can easily pass the seed. With parallel, you have to think harder about how you pass the seed. So I guess that's exactly what you're getting at.
Yeah, I think so. Yeah, I think so. And as I said, I'm not exactly a computer scientist, but I think I've at least understood that random number generation, when you do this distributed with workers that don't talk to each other, is a pretty hard problem. So I think that's one of the issues.
Cool. I was just wondering how worried I should be, actually.
Yeah. No, I don't think you should be worried about what you have done. It's more like, you know, that Future in principle will work on Google Cloud, and it might work on Spark and other things like that. And you, as the developer, don't have to care about what the end user will use your code for, so that they may choose whatever backend they want. And I think that's the part that might be hard on with the parallel package, for example.
Thanks. That answers my question.
Yeah, but if anybody else knows, I'll be happy to get a more exact answer afterwards. But you know, so how can Future make you a more efficient data scientist? I've outlined this talk along three different parts, and the first part is about some applications in statistics and machine learning. And then I will talk a bit about working with data, showing some of the file system operations you can do, dealing with data. And finally, I will point at some extensions of this. And in the first part, applications in statistics and machine learning, I will try to sort of keep a focus on the concepts, so that for the problems I present, parallel programming might be overkill, but in real life, you typically have pretty complex models. So what I'm trying to get at here is how you can use future to do things in parallel. So the first example I'm going to talk about relates to bootstrapping. And in R, there is this data set called empty cars. And let's imagine that we want to know if cars with manual transmission are more fuel efficient than cars with automatic transmission. And here's the data set. And then we have one variable called AM, which is 0 if it's an automat, and it's 1 if it's manual. And then you have MPG, which is the miles per gallon. So it's like how far does the car drive on a tank of gas. And we can check this with a GLM, with a logistic regression model. We can fit so predict. Actually, I've done this the wrong way. Have I? So what I'm actually doing here is that I'm predicting from the fuel efficiency. I'm predicting whether a car is an automat or a manual. And the automat was if it was a 0 and 1 was a manual. So the regression coefficient for the miles per gallon here was positive, which implies that manual cars seem more efficient, more fuel efficient, at least in 1974 when these data were collected. And this example is really stupid, but it's in order to like show the point of the parallelism here. So, okay, then you have this confidence interval, and you're claiming that manual transmission is more fuel efficient. But then your grandmother says those confidence intervals for generalized linear models, they're only valid if you have infinitely large samples. And you have 32 rows in this data set, which is quite a bit less than infinity. So you may not trust those confidence intervals. So, and the idea here is to get rid of that mathematical assumption in those confidence intervals by instead using something called the bootstrap. And the bootstrap is one of the like prototypes problems for parallel computing. So you sample data from your original data set with replacement, and then you refit the model. And you do this a number of times, large number of times. So the function works like this. So I made a little bootstrap wrapper. And inside it, each time I call the function, rather than using the original data, I sample from the rows of the data with replacement. So I generate new data sets each time. So this is the worker function that I'm going to fit a large number of times. And then I'm returning the coefficient for miles per gallon. And then using replicate, which is one of the functions in base R, I can do this. So I can say betas, that's my regression coefficients. Well, replicate 1,000 times this run bootstrap function. And because this data set is really small, there will be some convergence issues at a few of the sample data sets. So I just put suppress warnings around it to like avoid having 5 warnings getting out there. But from these, you get 1,000 regression coefficients, and then you can do quantile and say, I want the 95% confidence interval, which is then computed by R. So I have 2 lines of code that gives me the bootstrapped confidence interval. And if you have photographic memory, you might remember that the upper limit for the sort of the analytic mathematical confidence intervals was much lower. So the mathematical approximation used by the GLM function probably underestimated the confidence interval here. That was cool. So you could use the bootstrap. But then your grandfather says, those bootstrap confidence intervals are only valid if you have infinitely many Monte Carlo samples, which means if you do infinitely many random samples. So, okay, that's going to take some time, but maybe we should try 10,000 then instead of 1,000. So let's do 10,000 resamplings of the data. And this is where future comes in and might help us, because I have 12 cores on my system. And each of these bootstrap samples is run completely independent of all the others. So when I have 12 cores, in principle, so I might be able to reduce 1 hour of compute down to 5 minutes, because if I'm doing something that takes 60 minutes, if I split that up on my 12 available cores, then that should return 5 minutes. So in practice, you won't save that much, but with parallel computing, you might get this super fast. So what we do then, since I used replicate to do the bootstrapping the first time around, then I can load this package called future.apply. And this future.apply package provides a set of functions which extend this apply family in base R with a future underscore prefix. So you have future apply, future replicate, future map, future reduce, etc. All those apply functions, they have their equivalents in the future.apply package. And all I need to do is just put future replicate where I used to have just replicate. And then if I run this, it takes about 13 seconds. Now, by default, it runs sequentially. You see, there's one change in the code. I set future.seed equal to 4, and it has to be an integer, so I have to write 4L. So it took 13 seconds. By default, it runs sequentially, but what you can do is you can add a plan. So you write just plan, multi-session, and then you run exactly the same code. You just make sure you have run this plan statement first. And if I run that, those 13 seconds got reduced down to 3.8 seconds. So it goes pretty fast to get my 10,000 bootstrap samples. And then in the end, I go back to plan sequential. That's like a good programming habit, because then it's like turning down the cluster in a sense. So what happened here is that I just replaced replicate with future replicate, and I added a plan around it, and then I had a code that run in parallel. And we can check that when I ran it in sequential, that was the betas 1. And if I run it parallel, betas 2, they're all equal. So you get exactly the same results. And I get my confidence intervals, which when I use this even more, even larger number of Monte Carlo samples, my confidence intervals got even wider. So there is some reason to believe that there was like the mathematical approximation used by this logistic regression function in those original confidence intervals, they were a bit wrong. And the time I saved, so this is actually, so I got the wrong number here, but I saved about 4. So it took about 4 times as much to run this sequentially as it did to run it in parallel. In a real model, you would probably save a lot more, because what takes time in parallel computing is to like set up the jobs and communicate. So if each model takes very short to fit, then you probably don't save as much. But the models you typically work with in real life might take like several minutes just to fit one model. And then you typically get much more close to sort of the theoretical limit of how much you can save on running in parallel. So what happens here?
I'll just jump in here because Walder asked, is there any reason to use parallel over future then, other than the fact that parallel is part of base R? And someone has said that maybe if you've got some really legacy code, obviously, that could be one reason. But I'll let...
Yeah, I don't know. I mean, parallel is much older. So, I mean, I would assume that you might, for new development, you might want to use future, right? But you should probably know how to use parallel. I don't know.
Yeah, no, that's fine.
Yeah. So what happens here is that when I run plan multi-session, it starts new R processes on all my available cores. And then future distributes the jobs, and it makes sure that everything is identical running in parallel. And as I mentioned previously, it's not obvious that in this case I'm simulating and those cores are running in parallel. So it has to like give the right random number seeds to all those cores in order to make this completely replicable and platform independent. So other applications of this is, for example, permutation testing, where you try to like test a null hypothesis, typically in very high dimensional data settings, by permuting the data and refitting the model so that you construct a null distribution. You can also think of cross-validation, So for example, I would assume that packages like Caret would run stuff in parallel by default, but often, I mean, you may need more control. You have your own model that you're developing, and in these cases, you will have to like write your own cross-validation code, and then future could be like this type of approach could be very useful. And then you also have simulation experiments, and that's the topic I'm going to talk about on the next slide. Oops, then I have tidyverse here. So shit, that was so as you can see from the first so now I'm switching to another topic in data science, and as you can see from the first lines here, I have now attached the tidyverse, because in the previous approach I was with the bootstrapping, I used the future.apply. Now I'm going to show another part of future, which is called furrr, and this one uses the tidyverse type of programming instead. So I've loaded the tidyverse here. You just see all the messages. I'm going to talk about the typical problem in longitudinal data analysis, and it's summarized on the plot to the right here. And there is some measure of interest along the y-axis, and we have a bunch of kids, we can assume, that we have followed over time. And it could be, for example, their height, it could be their weight, their IQ, whatever. And your research question is whether those who start out low, do they grow more slowly than those who start out high? Or is it the opposite? So in other words, do people become more different or less different over time? So one idea for how to solve this problem is to estimate one linear regression model to each and every one, to each person, and then compute the correlation between the person's intercept and the person's slope. And if that correlation is positive, it means that those who have a high intercept, they also have a higher slope, so people become more different as they go older. And if the correlation is negative, it means that people become less different. So I have simulated the data set, and here you see I've also attached the tidyverse. And in this data set, I have an ID, the person's ID, and I have 3 time points for each person. And each person has been sampled at different ages, and I have some outcome Y, which I'm measuring over time here. That's my data set. These were, of course, just the first 6 rows. And then I'm using tidyverse code to fit the model to each person. And I'm gonna, even if this is not future, I will try to explain what's going on. So we have my data, and then I use tidyr's nest by function to get a nested data frame, so that I have 1 row per person, but that row contains a column, which is in itself a data frame. And then I use Perr's pmap function. Pmap is a functional programming function, which then takes this nested data frame, and then for each ID and each person's individual data frame, it fits a model. So this is the model. And this model is fitted once for each and every person in this data. And then I return this in a table. I return the person's ID, I return the person's intercept from the model, and I return the person's slope. So you get something like this. So we get out ID, intercept, slope for every person. So we have a regression for each person. Now, then I test core.test if there is a correlation between the person's intercept and the person's slope. And what I get is that there is a super negative correlation between intercept and slope, indicating that those who start out high, they grow much less. So that, for example, kids have a very high weight when they're 6 years old, they become more closer to those other ones. And those who have a very low weight, they grow more, so they increase their weight more. That's what this would imply. And the intercept slope correlation is shown also in the scatter plot, and we can see that there is a negative correlation. So those with a high slope grow much, they have a low intercept, they start low, and the opposite. However, in the data, it doesn't look like this, right? So if we look at the data, it looks more like, well, I can't see any strong correlation, but if anything, it looks like people actually become more different. They're like less spread at the low age than at the high age. So when a model returns something nonsensical like this, that's a very good time to do fake data simulations. Or in other words, we could ask, if I knew what the actual correlation was, would my model return the correct estimate? This is something that's a really important part of should be a really important part of everyone's toolbox.
So just a quick question about the modeling, I think, from Laurent. Why not do this multi-level modeling in IME4? And is it possible to use future with this IME4?
Yeah, that's where I'm getting, because this is a stupid model, and that's what my simulations are going to show with future.
Okay, so, that makes sense.
Yeah. So this was a stupid model, but then it is a model that's been. It may be fixed actually, but what we could do was that we could make some fake data simulations. We could simulate lots of data sets where we know the truth. And then we fit the model to each data set that we simulated. And then we look at how do these estimates, how are they distributed? Are they correct or are they way off? And this is, again, in this case, it might be a bit stupid, but in real life, like if you're making some complicated model, it's super important to know these things. Like if, for example, if my null hypothesis is true, will my model reflect that? Or on the opposite, like will the model, is the model able to estimate things correctly? And typically you need to do simulations to understand this. And here are the original data, just so you see it. So, but what I'm developing here is that I'm making one function for simulating data. We don't need to spend much time actually looking at this function, but let's just keep in mind I have a function which I can use for simulating data. Every person has their own intercept, their own slope. And this function returns a data set, which looks like the data set we already had. But in this case, I have constructed the function so that I know the truth. I know the correlation is 0. And then I have a function which analyzes the data. That's my other wrapper. And this function is exactly like the code I showed you previously for returning this correlation between intercept and slope. So there's no need to understand all the code here, but just remember I have 2 functions that do the work. And then, rather than future.apply, since I'm a more tidyverse kind of person, I would call furrr. Furrr is it comes here. Furrr is to purr what future.apply is to all the apply functions in base R. So furrr is the tidyverse type of parallel computing package. So you have future map, future walk, future p map, and all this. There are 30, 40 different versions of this for functional programming. And then I set up with tidyr crossing. I set up my simulation parameters. So I'm going to try this with 100 iterations. So 100 Monte Carlo samples. Then I'm going to have sample sizes 100 and 200. So using this tidyr crossing function, I get a data frame which contains, this is iteration number 1 with 100 samples, iteration number 1 with 200 samples, and so on. So I get all the simulation settings that I'm going to consider in my simulation parameters. And then, again, I let this plan multi-session. So this is perfectly parallel problem again. I'm going to simulate data set and then analyze it. And then I use, so I'm going to take this step by step. So this system.time around here is just to show how much time it takes. In the first step, I use future pmap DFR. So pmap is the general sort of map reduce function in the purrr or in the tidyverse. Underscore DFR means that it returns a data frame. And then the future in front means that it can run in parallel. And I give it this sim params, my data frame. And now for each row of this data frame, the following stuff is repeated. First, I simulate my data. Then I get my correlation by analyzing the data. And then I return a tibble which contains, okay, the setting, that was the number of samples. It returns the iteration number, and it returns the estimated correlation. And then in my options, I set the random number seed again, just so that I can be sure I get the same. I mean, it's not always a good idea to set the seed even, because it shouldn't matter for your conclusions, but sometimes, you know, you would like to have exactly the same things again. And again, I get back to the sequential. So this took about 12 seconds on my Mac to do this. So now if we look at the simulation results, so the true correlation here was 0. And in the estimated correlation was around -0.4 for both models. So this is a very strong sign that my model is off, my model is wrong. It does something wrong. And this has to do with the scaling of the H variable. And as you suggested, Bethan, it's probably better in this case to use a multi-level model. But this is the kind of things that are often much more subtle when you use complicated models. And with future, like even on your laptop, or if you have a cluster, you can get these simulations done so much more quickly than if you just do it in parallel. No, just do it sequentially. So in this case, we found out we should change this model. But now here comes another point. So look at this function call. So inside, so I do this future pmap. That's the top layer function that I'm using to run this in parallel. But inside here, I call my analyze data function. Now look at my analyze data function. This one contains pmap dfr, because inside each dataset, I fit one regression model to each person. So what if I instead had this? Inside my future pmap dfr, I could have had another future pmap dfr, or something else. You know, it could be future.apply, whatever, and it could be some sort of legacy function or function from another package that had future in it. And this is potentially disastrous, because then you're inside future and you run this in parallel, and then you get, like, in the next level, another function that tries to do things in parallel. And you might have even in another level something that tries to do things in parallel. And since you have one worker on each of your cores, then they might try to run this in parallel again and set up like jobs all across your computer that that makes everything break down. And this is a real problem and when we get back to sort of why we should use future. So future actually makes sure that these types of sort of infinite levels of parallelism never happen. So future makes actually sure that each top level worker only has access to a single core. So even if I had a future map inside of my future function, this one, when it came here, this one would actually see it as if there was only one available worker, so it would run sequentially. So here's an example of this. So where I use the future walk function, where I have an outer nesting with this I variable, and I have an inner nesting with the J variable. And then at each of these levels, so I set up, try to do this in parallel 2 times. So I say plan, multi-session, multi-session. This is the way to sort of set up that you want to have 2 levels of parallelism. And then I print out the process ID at the bottom. So if you have different process IDs, it means that you're running on different cores. And what we see here is that at outer level 1, whether it's inner level number 1 or 2, the process ID is the same. Even if I said multi-session, multi-session in the plan, and the same at outer level 2, I have a different process ID, but it's the same at both of those inner levels. So future really means, really protects against sort of inadvertently setting up lots of parallel jobs down at, like, inside the workers. And you have to work really hard to actually avoid it, no, to override it. But you can, however, if you need to, change how this parallelism occurs. So you can say, for example, sequential and then multi-session. here you're saying that the first level is sequential, the second level is multi-session. And then if you look at the process IDs, then we see that at outer level 1, you have different process IDs. But the process ID is the same at the inner level 1 and at inner level 2. So then we have now I've explicitly told it that this inner function is going to be run in parallel and the outer function is going to be run sequentially. So you can control this way. So that was a little bit about fake data simulation. Also talked about bootstrapping. And I hope, like, my point is that this is a tool that could be sort of used for much more complicated problems. But now I'm going to show you a little bit of what I'm doing in my own work, working with data. Another example. So, and I'm going to show you
files. Going, there was a note, and I guess you can comment on this, from Ego. I'm not sure how to say the name, sorry. However, if you are futuring some functions that internally use parallel, you may have a problem, I guess.
I would think so too, but I'm not sure, because I tried to make this and I wasn't able to figure it out. Because, for example, if you use this GBM package, which does gradient boosting, this package detects, like, even if you don't touch the options, it will try to use all your cores. But what it says on the documentation to future, I think it says that it sets this environmental variable for a number of workers to 1. But I'm not quite sure, like, how if it's like completely foolproof. But so probably you will have a problem.
Yeah, and some Mikhail has said that you also get this problem with parallel within parallel, I believe that's what he's saying. I can unmute you if you want to comment, Mikhail or Igor.
I was just saying, like, you have the same idea, the same issue. If you don't like try to parallelize within another parallelizer loop, like using either like the base package parallel, you will have the same issue. And the major issue is not that it won't work. It will try to work, and most likely you will just completely overpower your computer by using a lot of memory or CPU and more than you actually can. You will have a lot of air processes behind and so on.
And my point is that future does not allow this problem to happen. Even if in this case I really tried, like I said, multi-session, but still it doesn't allow it to happen. But I think, as was mentioned, that if you use parallel inside here, and this has to be tested by someone. I think if you use parallel inside there, you might be able to sort of override it. But with parallel in itself, like if I had parallel apply and then parallel apply, it has no safeguards. But future has safeguards, at least sort of to avoid that future itself runs into this problem. I don't know if that made sense. So it's definitely an improvement compared to parallel. And there is on the documentation for so in the futureverse.org, there is like several sessions about this. And at least for some parallel backends, I think so like other parallel backends than future itself, it sets some environmental variables that make it appear as if there is a single core. But I think for parallel, this doesn't work.
Nice.
Yeah. So now we're talking about modeling. Now I'm going to talk a little bit about working with data. So we've introduced future.apply. We've introduced furrr. Now I'm going to continue a little bit with furrr and introduce a few new things. So, and here's a data science problem that I have, or data management problem. So I have MR images, like magnetic resonance images of brains. And these are really big files. So, and I have in the data, I have one directory per scan. So essentially every person that I have in the data set has one directory after it's being processed. So if I count the number of lines or the number of directories, I get 40,021. That's the number of observations I have. Now, each subdirectory itself has even more subdirectories with more information. So if I look at this person with ID that I just made up, so if I go into this person's directory, there is 3 more directories. It's label, it's scripts, and it's surf. And this is the end results of statistical algorithms that have been run in order to estimate how this person's brain looks like. So inside there again, there is this directory called surf, and this directory contains the data that I need. So for example, it contains the area of your left hemisphere, and this is like a very dense map over 100,000 pixels, showing you the area of your cerebral cortex on your left hemisphere. And then we have some smoothed version, and we have the thickness, and so on. Now, very rarely it happens that some of these directories are empty, because this algorithm that was used to compute these variables, it failed. You might also, and I might also sometimes find that there is, they're not empty, but there might be some warnings in some text files in there. So I need some way of accessing all these 40,000 directories. And I'm not very good at bash scripting. So my go-to is then to use R. So I need to find out sort of where did these failures happen, and I need to find more information about this. So I have, and in order to do this, I'm going to show you a little bit how I approach this problem with the future. So I created some test data. So I made my own UKB test folder, which had the same structure as the data itself, and I copied some mock data in there. So you have so here we have two persons. You have subject 1 and subject 2, and they have their own directories. And we're going to work through this. Sorry? Now, in R then, I can make some prototyping. So I have my directory, which is where all my data are. And then in order to get all the directories for each person, I can use the list files function from base R. And I can say that it's going to include directories. And in real life, I might have some more pattern, like some regular expressions here to make sure I get exactly the directories that I want. But I get all the directories that contain the data. Now, on my laptop, not a cluster or anything, I can then prototype code using, since I am a tidyverse person, I can use map DFR to sort of map through or work through all these directories, check. So I can first list the files in the person's directory. Well, this is first to create the path, and I find all the files in this person's directory. And then I check, does the person have 0 files? This means so if there are 0 files in this person's directory, it means that it's missing. Then some errors happen. And then I return back a tibble, which contains the person's ID, which in this case is the path to the file. And I return whether it's missing or not. So this is like pure tidyverse functional programming. The only exception is that I have future underscore in front of it. And I test this. I could even test this on the read data just by subsetting. I can take rather than taking the 40,000 directories, I could take the first 10 directories, check my code is working. And then I'm happy when I know that this works. I've tested and it looks like it returns the right results. So what I get is something like this. I get that subject 1 is not missing, subject 2 is missing. Then all the changes I need to do to this data is to add plan multi-session in front of it. And I also need to save this directory, now this output. And then I have a script that I can run on my huge computing cluster, which is able to handle these huge amounts of MR data. So what I do is that I have this script that I developed locally, I tested it, I know it works. And then I use something called Slurm, which is a job scheduler on a big computing cluster. And I say, I want 60 CPUs, so my 12 on my laptop is not enough, and my data is not even on my laptop. They're on a secure cluster. But my script is exactly the same script that I could use with my mock data that I've tested and I believe it's working. I just need to run it in batch mode. So I say rcommand batch and some options and script.r, and do this with 60 CPUs. And then I get my results. And that's, I think, the third advantage of Future is that it's just exactly the same code, tidyverse style, and it could be future.apply if you're more into base R. And you can run it not even on your laptop, you can run it on a cluster or somewhere else. So that was one hint at how you can do data manipulation. You can also do all this, all of these functional programming functions in furrr can also be useful if you do a lot of sort of data wrangling, SQL type, because then you can just add future in front whenever you do lots of complex operations on your data, and it can be run in parallel. So I'm going to talk about some extensions to this. So one of them is package development. So if you have anywhere in your package, so if you're developing an R package, and anywhere in your package you're using apply, mapply, and so on, or you're using the purrr functions to do some work, then you can just add or replace it with future apply or future map in your code. And all you need to do is to make sure that you have this furrr or future apply in your imports in your description file. All the code else is just the same. Now, your user by default doesn't need to think about this, doesn't need to know that you're using future. Your user can say library your package, and then call your function in your package, and it will run sequentially. However, the user can choose to do this in parallel by attaching future, and then saying plan multi-session, and then call your package. And then the user can see if this leads to speed up or not. So it might be that it might be that the user has a problem where it pays off a lot, and then the user can add this. But the point is that there is no more. The user doesn't even have to like give an argument to your function. Just these two lines is all that has to be added. And there's an example from I wrote my, but it should be our metagam package. It's a package for meta-analysis by myself and some co-authors. And that's a package for analyzing, meta-analyzing, when you have nonlinear functions like this. So here we have 6 different results or models estimated on 6 different data sets. And we want to have sort of a meta-analytic estimate of the overall function here. And in this package, we actually added this option. So I'm just going to show you the code, how it works. So in one of the sort of examples in the package, you can get an argument with your models that you have fitted, and then or that other people have fitted, and then you want to do a meta-analysis of these models. So by default, you just do a normal call to this metagam function, and it runs sequentially. If you want, you can add future, then plan a multi-session, and then run the same code. And in this case, it was a really bad idea because it ran much slower. So it seems like in this case, actually setting up the worker took a lot more time than running. But there are, of course, lots of examples where it's the other way around.
Can I break in there? There's a couple of questions.
Yeah.
Gerard was asking, how do you store data to access them from the cluster? I think more about what's a good way to do this potentially.
Yeah, how you store data at the cluster?
Yeah, how you store data that you're accessing from the cluster.
Oh yeah.
I mean, to store it distributed, or example, for example, at an S3 or HDFS or something like that, or is it locally stored at some edge node?
It is. I have to answer the best I can. In the examples that I have shown so far, it has access to your own file system so that it works exactly as you do it sequentially. But I don't know. I assume that this can be harder if you do it on Google Cloud, for example. But what I've done, for example, is you can, for example, have, I think I had an example here. It works. Let's just see if I find it. No, it was here. Yes. So here at the cluster, you can save, but also inside of this future map function, you can save. But then you probably need an iterator. You need something like the index of the job to distinguish the files from each other, so that you have like job number. And you can use that to define the path to the file that you're saving, and then you can have save RDS inside here. And I'm going to talk a little bit later about how it might also answer your question that Future uses something called static code inspection to see which objects that should be exported to each worker. So I'll get back to that maybe, I think. Yeah, I'll get back to that in a second, and then let's talk about that more in the end. But it should work out of the box exactly as if you're running sequentially.
So Anastasia, who I gather is your colleague, is mentioning something about UIO clusters have specific disks on the local system that they connect to, so that some of this should be UIO specific, I gather.
Yes. So for example, but when I run it on my laptop, then each worker has access to the file system. But I guess I think that's mentioned as one of the like open challenges in Future is connection to databases, for example. So I can't really give a good answer to that in general, unfortunately. But it does return an object. So if you use future map or future.apply, it does return like the object that your function is returning is there, and the data that you're going to use at the cluster, if it's not really big, then you can probably just add that as an argument to your function. But with big data, I have no idea. I'm sure it's more complicated then.
Yeah, so we've got a question, but they say that maybe it's better to wait to the end about using Future with multi-thread R packages such as data table.
Yes. So Future has support. Well, let's just keep that in mind for a little bit.
Okay.
Multi-threading, yeah, because I had just one slide before we get there.
Oh no, that's totally fine. That's totally fine. I think we had one other question. Let me just try and find it. If I run my own function which uses multiple other R packages in a cluster, does it call it automatically attach all the right packages to the cluster sessions? Illustration I have the for each package mentioned.
We'll be there in one slide.
Oh, perfect.
So this person is really really paying attention. Yeah.
Okay.
So just remember those questions.
Waiting in anticipation.
Yeah. So before that, just what I've shown you now is typically even the thing I sent to the cluster, and you saw my cluster script for processing this data, it was still just pure R. So I set up a cluster, or I set up my R job to have access to 60 cores with the Slurm script. However, there is something called future.batch tools, which would actually let me not have to specify these Slurm scripts with my bash files, but rather just do this in R. And this is, so future.batch tools supports the types of backends supported by the batch tools package, which I have never used, but it's stuff like Torque, Slurm, Oracle Grid Engine, and this is very well documented on this website. In addition, they have on the roadmap backends for Amazon Web Services, Google Cloud, and more. So I think many of these things are coming. But the way I understand it is that then you can get, like, you can submit some of these jobs and set up the whole sort of queuing system from your R session rather than using Bash, and that is nice for those of us who like R. But then, yeah, and I have, so this is getting to this data table question. So not really, but I've always shown plan multi-session so far. There is an alternative called call R, and this is from the documentation, which says that when you use call R future, each future is resolved in a fresh background R session, which ends as soon as the value of the future has been collected. In contrast, multi-session future are resolved in background R worker sessions that serve multiple futures over their lifespans. So the way I interpret this is that when I use multi-session, it starts up a lot of workers, one on each core, essentially, and then it runs many jobs on those workers, whereas future.callr starts a new session each time. And that, it says something like that there are no good benchmarks, but that's has some advantages, I would guess. So what you would do then is that rather than saying plan multi-session when you call your function, so here I have an example with future.apply. So you can do plan sequential, you can do plan multi-session, and you can do plan call R, and they all work the same. So call R and multi-session then use the same course. There is one more, which is called plan multi-core, and this one is using threading. And this is not available if you're using RStudio, and it's not available on Windows. And I have a feeling that it's not in general recommended. This has to do, I'm not even going to say what it has to do with because I don't understand it. But I think that's a little bit related to this data table, and I have no idea how data.table works on future, if this is using, yeah, because that's, that's really efficient because it uses threading. So if anybody knows, I would appreciate knowing the answer, but I have a feeling that this hyper-threading is not recommended when you're using future. So this future option called multi-core is then, because of this, disabled if you're using RStudio, and it's not possible to do it on Windows. I think don't have much more to say about that actually, because I don't know. But then here comes the other thing about which packages to export. So one of the things that can fail is that future uses static code inspection. So it's like it reads through the code using the globals package to identify which variables and which packages each worker needs. And it is possible to make this fail. And here is one example. So, and this is the only example that came to my mind because it's the one that I've seen. So Metaphor is a package for doing meta-analysis. And we don't need to understand what's going on here, but this is just one example taken from the Metaphor package. You have a data set, and then you fit the model using a function called RMA, and you get this model called mod. Now, assume, just for whatever reason, that you would like to predict from this model in parallel. So you have the model, it's in your R session, and then you call future map. And you're saying, okay, I'm going to run it only once, and this is just in order to show that it's possible to get an error. So I'm going to do one run where I'm predicting from this model. Now, this is failing because predict uses the is a generic, it's an S3 generic. So what you would write here is that it calls stats predict. And then when it sees that this object has S3 class RMA.uni and RMA, it looks for that function, which is the predict function from the Metaphor package. However, static code inspection is not able to see that mod is an object of class RMA because it doesn't evaluate this object. It only sees predict. So well, in principle, it exports predict from stats to this worker, but it does not export this metaphor package, which contained the S3 class that was necessary to actually evaluate it. And when we're at it, you can see this tilde here. This is just to show that when you're using furrr, like future map, you don't have to write functional x. You can use this inline function operator in the tidyverse. So I just use a tilde here. But this is a very silly function, just so you know it, because mod is not an argument to this function. But mod is available, so it sees the static code inspection, sees that mod is there. So mod is exported, but not the package used to evaluate it. So what we would have to do here is that I would say in the options, dot options, I have to say furrr options, and I say packages equals metaphor. So I have to explicitly tell it that I have to attach the metaphor package. And there are other, so in these furrr options, you also have, I think, not sure what it's called, objects or something, another argument that you can use to specify which objects to export to each worker. And the same thing applies when you use future.apply, for example. So here's an example where it failed. So if it fails, this is the type of things you might look for, because it's not foolproof. So I think that was what I had. If you want to learn more, I really recommend going to futureverse.org. And one of the cool things that I didn't have time to talk about is Progressor, which is a package for making progress bars, which is often useful when you're sitting and waiting for computations to run. So thanks especially to Henrik Bengtsson, who made this fabulous set of packages. And thanks to all of you for asking very good questions. And let's see if there are more questions.